to compile this information, what we have done, what should be the way for the future. We are doing some work related with this also in the European group, call it Marine Energy Board. So I hope we will have a good report also on what has been done, but at European scale. And we also continue to have our annual report of the IEA-OES, so where we get the information from all countries, but a short summary.
I noticed that the US funding for the marine hydrokinetics has very much increased recently. I mean, a couple of years, they almost 50% of funding for the MHK increased. So I'm just curious to what's going on in US side for that much funding increase in ocean energy.
Yes, it's increasing every year, but this is especially this year. I think they had several
recording in progress.
Several prizes for so many candidates could apply with an idea for wave energy or related with also with other markets, ocean energy for
recording
ocean observation, or for, so they have many different initiatives, and also a big test center with much funding for the development of the test center in, I think, in Oregon. So that's interesting.
Yeah. You know, actually, we applied for that funding from US that the combined, the associate with the one US engineering company, and the one of our previous project key technology was developed, and it was applied with the US company for the US funding, but actually we failed. But there is looks like there are many chances these days for some of the field tests for the wave energy device and some other tidal energy device too.
Recording in progress.
So you were in a consortium with the different entities to apply for the US funding. Okay, good. I think we are. I'm not sure if we are online now. I mean, maybe.
Thank you to our honor sponsor, INDO EBTKE CONEX 2021. Main sponsor by Mentari UK, Indonesia Low Carbon Energy Partnership. Platinum sponsor by ISED. Also, our platinum sponsor by the Swiss Confederation. Gold sponsor by Oil Palm Plantation Fund Management Agency. Silver sponsor by Swedish Energy Agency and Business Sweden and Bukit Asam.
Assalamualaikum warahmatullahi wabarakatuh. Selamat siang Bapak Ibu, saudara-saudara sekalian. Good afternoon, our guests, highly respected speakers, and all audience. It is good that this afternoon we all gathering here in Ocean Energy Forum, part of EBTKE CONEX conference and exhibition. And right now we have a lot of we have nine speakers from all over the world. So this time here in Indonesia at afternoon, but some of our speaker right now is very early in the morning. We have let me check first our speaker. First one is Dr. Ana Britomelo is here right now, Dr. Ana, yeah. And then second one is Dr. Keong Hong from South Korea. Dr. Keong is already here. And then Mr. Andrew Scott from CEO of Orbital Marine. Mr. Andrew, already in, please.
Yes, I'm here. Good morning.
Good afternoon. Good morning. Yeah, thank you. And then Mr. Simon Forrest, already here from CEO of Novas Innovation.
Yes, good morning. How are you doing? Good afternoon.
Thank you. Thank you. Good afternoon. Good morning. And then Mr. Ahmad Mukhlis Firdaus from PT SPS Indonesia. Pak Dr. Ahmad Mukhlis?
Yes, Pak, but I have problem with my video.
Oh, okay, thank you, Pak. And then Mr. Ian Johnston from Director of Aquaterra.
Yeah, I'm here.
Thank you. Thank you. And then Mr. Jonas Kamp, CEO of Wave for Power Sweden. Hello? Mr. Jonas? Or maybe he will come with later. And then Dr. Zainal Arifin from PLN, Indonesia. Pak Zainal? Maybe we'll follow later. And then we have also from Malaysia, from UTM Malaysia, Professor Umar Yaakob. Ladies and gentlemen, actually this conference is annual conference. We have been doing this for 10 years. So this is 10 Indonesia EBTKE CONEX. And we have 9 speakers from various backgrounds. We will divide into 2 sessions. First one, we will have 4 speakers, and then we break about 10 minutes, and then we will have second session until about 5 p.m. Indonesian time. So we will have 2 sessions. In the first session, I will serving you as a moderator. I am Mukhtasor from ITS, Institute of Technology, 10 November, Surabaya. And then at the second session, the moderator will be Dr. Dendi Satrio from ITS Surabaya also. So without any further, we'll start. First speaker is Dr. Anna. So Dr. Anna is I'll share her curriculum vitae. Dr. Anna working at WaveEC, and she will be delivering a topic on the status of international development of ocean energy, policy, industrial, and economic aspect. She is very active in ocean energy, especially she is serving in International Energy Agency of international collaboration on ocean energy system. And she is a senior advisor of the board and heads of strategic study from 2019 to until now. And her background is a PhD in mechanical engineering. I think she has been a lot of work on policy discussion, industrial development, and economic assessment related with ocean energy, under ocean energy system. So we will learn a lot from her. So Dr. Anna, the time is yours right now.
Thank you, Professor Mukhtasar. And thank you so much for the invitation to participate in this conference. I will share my presentation. I hope you are seeing it now in slide. Okay. So I will focus my presentation on international collaboration, and I will speak about the work that is being done by an international organization known as IEA-OES. I work at WaveEC, and one of my roles at WaveEC is to be responsible for the communication and for the secretariat of this international organization. Within the International Energy Agency, the IEA, there are different groups for collaboration in different topics, for all energy issues, and also for renewable energies. So there are one group for geothermal, photovoltaic, bioenergy, hydropower, wind energy, and one specific group for ocean energy, the IEA-OES. And the IEA-OES covers all sources of energy, of ocean energy, so wave, tidal range, tidal and ocean currents, ocean thermal, OTEC, and salinity gradient. It does not cover offshore wind because offshore wind is covered by the specific group on wind energy. This group was created in 2002 by 3 members, Portugal, UK, and Denmark, and now we have 23 members. The participation in this group helps to build connections between governments, industries, and it is a strong network of experts able to expand national research capacities. There is a diversified representation of interests in the EXCO. So the executive committee, the EXCO, has members from governmental departments, utilities, governmental agencies, industry associations, from the academia, from energy agencies, which is it's a benefit, totally acceptable manner. We have a work program that is approved by the executive committee, and it covers very diversified topics. There is a set of projects running, one on environmental effects and monitoring efforts, led by US, a study on the cost of energy assessment for wave, tidal, and OTEC. This is a report, study that was done by a consortium of different entities. We have a project on the International Evaluation Framework for Ocean Energy, discussing guidelines for the evaluation of the technologies. We have a study running on the assessment on jobs creation on ocean energy. And the most recent project is on alternative markets on ocean energy. I will then focus on some of the work of these projects. There are also 3 working groups, one on wave energy, on numerical modeling, so comparing different codes that have been developed by different organizations. A similar group exists on tidal energy, and another one on OTEC. We also support the development of databases, so collection of information from all country members. TECIS is a very known database on environmental data, on ocean energy, also offshore wind. We have a worldwide WebGIS database on our website with information from all projects around the world. We have been collecting information on consenting process for ocean energy in different countries, and there is an ongoing collaboration with EMEC, the European Marine Energy Center in UK, to develop a database with all test sites around the world. On the most recent paper published by IAOES was a white paper on OTEC. There is a group working on this, on the preparation of this report, including India, Japan, China, Korea, Singapore, and France. And this was resulted from the need to have a good knowledge on the state of the art of OTEC and how to move forward, what is needed to progress on OTEC. The report contains very useful information on showing that the biggest barrier is financial and not technical. And there are 2 plants that already show that it's a reliable source of energy, the Hawaii Natural Energy Laboratory in the Okinawa Deep Sea Water Research Center. So the big step is to have the financial guarantee to move behind small demonstration plants to pre-commercial prototype units. And it's vital to encourage international cooperation in this field. On environmental issues, this is an ongoing work. It collects information from many projects developed around the world. It's known as TETIS, is the name of the database, with over 3,000 documents. It's led by the US Department of Energy and has been implemented by PNNL. 15 countries are participating in this task. They are analyzing, there are a group of experts from different countries analyzing the information that is presented in this website, and also organizing webinars on different topics related with environmental issues. On consenting, we have produced a report that gives a succinct overview of current practice on the consenting process in different OES member countries, investigating the main barriers associated with permitting and licensing. And in this report, we have the view of the developers that experienced this process. And also there are particular attention is given to marine spatial planning. A recent work was done on building consensus on evaluation, so to have a guide, an ambiguous process to evaluate all ocean energy technologies, and to guide the appropriate and robust activities through the technology development process. This is a very useful guideline for supporting decisions, so for regulators as well as for developers. From the concept creation of a technology to commercial scale, there are different steps, and all these steps need to be evaluated on with consensus before going from one step to the other. This work has been done with Energy Scotland, by the US Department of Energy, European Commission, and involving all members. And it's been applied, is now being applied by some funding agencies. We recently started to look for different markets, opportunities for ocean energy. So the dominant market is the utility scale grid electricity generation, but we also identified other markets like islands, also for desalination and for off-grid applications. There is in our website a set of interviews that show for different stakeholders that show success cases or opportunities in these different markets. We have done a study on the ocean energy in islands, looking to the barriers and the recommendations in 3 different locations. One, this was based on 3 workshops were organized, one in Southeast Asia, another one in Europe, and one in Hawaii. And we come with a set of conclusions. What are the main barriers to progress with ocean energy in islands, related with the technical supply chain, with the social environmental aspects, with financial and economics, and legal and political issues. Based on these barriers that were identified, there is also a set of recommendations. The ongoing study now related with different market opportunities is started on the offshore aquaculture sector. We are looking to the energy requirements of this sector, how to develop sustainable offshore aquaculture, looking to potential opportunities between ocean energy and aquaculture, looking to different case studies around the world, and coming out with recommendations, identifying what are the challenges. This work is being led. Okay, I think for a minute I was muted automatically. So I was talking about our study on offshore aquaculture that is going on, and the next study will be on desalination, a similar study like the offshore aquaculture. So looking also to understanding the potential and assessing the technology and looking to the way forward. On our website, there is a worldwide web keys database with providing detailed information on energy resources and related projects. It comprises information on ocean energy facilities, resources, relevant infrastructures, and geographical information. Just a general message of how OES sees wave energy progress. We see that there are several full-scale devices in the manufacturing phase of preparing for deployment. There is a continuous evolution along the TRL technology readiness level scale, and the first farms are being designed. There is a number of potential breakthroughs that have been developed and being integrated in these new projects. There is still a wide variety of wave energy technologies, so no consensus yet for a specific technology, but also there is different opportunities to explore the potential of the waves offshore, near shore, or shoreline. So maybe no final convergence for a single device is needed, and there is extensive testing programs. Extensive testing programs are still required to progress with this sector. On tidal current energy, we are approaching a design convergence. We are approaching commercialization with deployment of full-scale devices in first arrays. Progress has been demonstrated by operating hours accumulated and electricity generated, and we need for further technology investigation and demonstration. We need long periods of time of testing. This information is published in our annual report every year, and also publications specific for each technology. Finally, to say that this, as I started in the beginning, this work is done by WAVEC in Portugal. WAVEC is a non-profit organization promoting the development of marine renewable energy, supported by R&D, innovation, and transfer of knowledge. We are a team of 20 people with backgrounds on marine biology, engineering, and communication, and we work in close collaboration with universities, authorities in industry. Our business area is marine renewable energies, but we are also looking to offshore aquaculture because they share the same problems, and also other ocean engineering solutions. I think I finished my time, and thank you for your attention.
Thank you very much, Dr. Anna. So you presenting very nice presentation and talking from OTEC, tidal, and wave. So maybe many of our attendants would like to ask about the progress in ocean technology, industrial, and economic aspect. But we will put the question and answer at the end of this session. Okay. So thank you very much, Dr. Anna. So let's move to the second presenter, second speaker, Dr. Keong Hong. Dr. Keong Hong, he is working in Korea, South Korea actually, and he will be presenting to us on the Asian wave and tidal energy technology and industrial development of ocean energy. Sorry. Dr. Keong Hong will be presenting on the technology and industrial development of ocean energy from perspective from South Korean and also international. He is working at CRISO. CRISO stands for Korea Research Institute of Ship and Ocean Engineering. And this is his experience. His background is in PhD from Texas A&M University. I think it is time for you, Dr. Keong Hong, please.
Thank you, Professor Muktasor. Let me. Okay. I'm very glad to have this great opportunity to introducing the status of ocean energy development in Korea. I changed the title a little bit. I'm sorry for that, but I will briefly introduce overall situation in ocean energy development in Korea. Then I will focus a little more details on wave energy technologies, which has some of the significant progress recently. My talk will cover these contents. Let me start with the national strategy for the carbon dioxide zero, which was announced by Korean government in 2020. This national plan targets carbon neutral society in 2050. So currently in Korea, CO2 emission is almost 270 million ton. But this national plan targets zero in scenario A by 2050. But in scenario B, still 20 million ton of CO2 equivalent is included. Among these national plan, renewables account for almost 890 terawatt hour annually in scenario A, and scenario B is a little less, 736 terawatt hour. Among those renewables, ocean energy needs for 2.5 gigawatt installation by 2050. Among those ocean energy, you can see in pie chart each sector of ocean energy contributions. For example, tidal current contribute 600 megawatt, and the wave in coastal area is 50 megawatt, and the offshore 220 megawatt. Also, it includes a hybrid system, which wind and ocean energy hybrid systems, 310 megawatt. Also, tidal range is included in this plan, 1.35 gigawatt installation. Market incentive system for renewables in Korea based on RPS, Renewable Energy Portfolio Standard, and REC, Renewable Energy Certificates. In this certificate, kind of incentives adding to the system marginal price. So renewables get additional incentives for this RPS system. In this, the market incentives, tidal current and tidal barrage is included already, but OTEC and wave energy is not still included in this, the RPS system, because they think still it's early stage for market entry for the renewable, the society. This shows some of more details on the national roadmap for the wave energy development. basically, we recently focused on the infrastructure construction for the sea test for different types of wave energy devices. And currently, in 5 years from now, 5 years focused on kind of a megawatt class pilot plant. Then next 10 years, pilot farm about 45 megawatts. Then eventually by 2050, about 225 megawatt wave energy farm is planned for the installation. In early stage, R&D and pilot plant stage, funding solely from the government, then more involvement of local government and industry, like the wave energy converter industry and utility company also involved. Eventually, the commercial stage industry leading funding is expected in this roadmap. Tidal current energy development has a similar roadmap for the development, but they are expecting tidal energy device has a better chance for the early commercialization. So the overall time schedule is a little faster than wave energy cases. Also, the installation capacity is bigger than wave energy cases. OTEC, unfortunately, OTEC case, we don't include it in OTEC installation for the national plan for the carbon dioxide neutral strategic plan, because they think still OTEC technology is quite early and some uncertainty there for the commercialization at this moment. They are considering some of the hybrid system, R&D funding, also some pilot plant is planned for the sea test. It's basically current development focused on the wind wave hybrid system. I'll briefly introduce some of the key projects in each ocean energy sectors. Firstly, wave energy devices development in Korea. In 2016, we installed breakwater type of OWC devices in Jeju Island. It's a couple of device capacity of 250 kilowatts. And it is still in operation. And this facility is actually expanded for the sea test bed, which was constructed 2019. So now this facility is a wave power plant, also part of the infrastructure for testing of wave devices. And recently we constructed another OWC devices in remote island, but this device has some features with the energy storage system combined with energy storage systems installed to the microgrid in remote island. So power control is quite important in this unit. I will introduce a little more details later. Also, we developed some wave-activated moving devices like a pendulum wag and arrayed wag. Pendulum devices completed in 2016, and it had some field tests shortly. Recently, we also developed this kind of arrayed wave energy converters, which target 20 devices together in one platform. Each module has a 50 kilowatts capacity. Tidal energy devices. first device installed in Korean coastal sea was Ultormok tidal current power plant, which has a couple of 5 kilowatt helical turbines. This facility also expanded for the sea test, part of sea test bed for the tidal energy devices, which is being constructed right now. Another 200 kilowatt active control tidal current turbine, which has a yawing control depending on the tidal current directions. And the most recent one is 1 megawatt device, which has a variable pitch control, but yaw is a fixed types. So it's being designed right now. Then in a couple of years, it will be manufactured and be tested in Korean Sea. Okay, OTEC, the project. First, OTEC for the power plant is a 20 kilowatt one that is called KOTEC 20. It was completed in 2013. Then hybrid OTEC, which utilized some other heat resources together with the seawater temperature difference. So it was completed in 2014. That was a capacity of 200 kilowatt. And the most recent one is KOTEC 1000, which target 1 megawatt gross power and 500 kilowatt net power. It was completed in 2019 and tested in East Sea of Korea at the nearby Pohang city. This system designed for 1 megawatt gross power at 24 centigrade degree temperature difference. And the performance test in 2019 at sea, target was, Korean coastal water has a very limited temperature difference, so we cannot test it in full capacity. But at the test, we target at 20 centigrade degree, 500 kilowatt gross power at the 2% efficiency. Actually, we get is 338 kilowatt gross power at the 18.7 centigrade degrees. So still quite a nice result from this field test. Korea has huge potential for the tidal range power plant, particularly west coast of Korea. One of the big project was Sihwa tidal range plant, which completed in 2011 and in continuous operation now. It has a capacity of 254 megawatts. There are some other bigger potential sites in Korea, but there is big obstacles, big barriers to overcome for the real construction of this tidal range power plant. One is that the environmental issues, this area is very sensitive for the environmental impact. So that is a big issue. Another one is the acceptance by local residents. So those two are very big issues for the further development of these tidal range plants in Korea. Screen is not moving. Sorry, screen is not smoothly working.
Maybe it's the file is quite big.
Yeah, probably. Yes. From now on, I will focus on the wave energy technology progress, mostly recently completed. One is the KWTEC. KWTEC is Korea Wave Test and Evaluation Center, which is basically test bed for many different wave energy devices. Its location is Jeju Island and funded by Ministry of Oceans and Fisheries, and operated by CRISO, my institute. Number of buses is 5, including Yongsu OWC power plant that I introduced already. Also, a couple of 20-meter water depth berths, then 40-meter and 60-meter. Total capacity is 5 megawatts, but the 2 megawatt maximum in each berth. It's quite useful for the wave energy devices. Also, it can be used for the floating offshore wind turbines. So actually, we have a plan for the field test of 8 megawatts floating offshore wind turbine in 2024. It's already funding is there, and there is one of the big projects in Korea for the floating offshore wind turbine development, and this test bed will be used for this test in the future.
Oh yeah, this is moving now.
Moving, but it's skip one more slide. I don't know why. Okay, let's start. Okay, this is the Mungni, the OWC integrated with the energy storage system. It's OWC device, but it's developed for the application to remote island. Remote island has usually diesel, the power generation system, but usually this remote island has issues environmentally clean energy resources is the prepared by government. So the energy resources like a wave is quite important in this area. Also, grid connection is the issue. Usually they have microgrid. So energy storage system and clean energy resources like wave energy is a big favorite, big preference for the Korean government. Also, electricity price is quite high. So even though wave energy is still cost is quite high, it's very competitive in these areas. So as you can see that we use the energy storage system using batteries. Then this is the plant for the OWC devices. This is the power control unit, including the energy storage systems. Also, this system is much more improved from the Yongsu OWC in technical point of view. And this we did some experiment for this system design, and it was used for the IAOS wave modeling group. They do several different types of wave devices, the numerical simulation by many different organizations for the comparison of results and better simulation tool development. And our experimental result used for the comparison of those numerical analysis. Sorry, it's not smooth operation. This is the types of wave energy converters. We call it WABUI, weather adapted array buoy. Basically, this platform is depending on wave condition. Platform angle is bearing, so adapting weather conditions. Also, this is used a turret type mooring system, which means weather vaning is automatically induced by these turret systems. We did some experiments at the real sea. I mean, not integrate whole system, but just key modules of this development tested at sea using barge installation. One of the key issues and the key technology for this power the control systems. One of the key problems in wave energy devices is the fluctuation of generated powers. You can see in this, the black color is rotor power. That means wave force fluctuation is directly influenced to this, but the actual PTO power and the generation power is quite stable compared to the wave power fluctuations. So we developed this quite stable control of the power generated by wave forces.
Dr. Keong, 1 minute left, please.
Okay. You can see some more details of this peak fluctuation. This is the Mungni OWC, Yongsu OWC, and this one is for the new device. So quite difference between that. We are developing kind of integrated software package called Wave Energy Converter Analysis Program package, which including some of the data like meta-ocean data and the platform motions, generator and power control systems, even including some structural analysis for the ultimate strength and fatigue life analysis. Also combining with the pilot plant, it can be digital twin technologies. So we are developing kind of a integrated software package for the wave energy system design and operation. This is some kind of a comparison between well-known vacuum and wavedyne device developed by DMVGL. And currently, OWC devices is not included in vacuum and wavedyne, and we are developing also, we do estimating annual energy production from this software package. Well, I will just mention two things in my concluding remarks. One is that the niche market approach for wave energy devices, because wave energy devices still cost is quite high. So niche market like a remote island, which has a very high price of electricity, also combined with the breakwater, which has, so we don't need any the casing structure cost for the wave energy generation. So niche market approach is one of the things. Another one is some innovative new technology combined with the wave energy technologies. One of the new projects developing in Korea is a marine green hydrogen project, which utilize wave energy electricity to generate hydrogen in sea. So this kind of new innovative breakthrough technology combined with the ocean energy is quite important in the near future. Thank you for your attention.
he covered a lot of technology from tidal, wave, OTEC, and also hydrogen. Maybe some of you have question to him. Please wait until at the end of this session, and you can also chat in this chat. Type your question or your comment to Dr. Keong Ho. Okay, let's move to the next presenter. We call for the next presenter is Mr. Andrew Scott. Are you here, Mr. Already? Test?
I'm here, yes.
Okay. Mr. Andrew Scott, he is a Chief Executive Officer of Orbital Marine, and this is his experience. A lot of experience from many different companies, and also from Ocean Energy, from Orbital Marine, and also IG Wave Power, Polamis Wave Power. So he has a lot of experience on this field. His background is in MSc in energy from Harriet-Wood University. So time is yours, Mr. Andrew. Please.
Well, good afternoon, everyone. Hopefully you can see mine.
By the way, the time is 15 minutes, so please keep in with the time, please.
Certainly, I'll see if I can actually get through it. But good afternoon, everyone. I'm the Chief Executive Officer of Orbital Marine Power. As introduced today, we are a technology developer for tidal stream technology, which we believe has significant global market potential, arguably the largest of which could well be in the Indonesian region. So delighted to have the opportunity to give you a bit of an overview of our technology and what we do. So we're a Scottish-based company, and we've been developing this technology for over 20 years. It is a unique proprietary technology in that it is not seabed mounted, and it is floating. So it's moored. You'll see more photos and animation in the future. We have over 100 years of accumulated experience in delivering tidal stream technology, with patents covering the key bits of the technology. Over those 20 years, we've consistently delivered flagship projects. That included the world's first grid-connected floating tidal turbine, which was a 250 kilowatt unit. And we also then, in 2015, delivered the world's most powerful tidal turbine, which was a 2 megawatt unit. So you can see here on this slide, our 250 kilowatt unit on the left-hand side, which was grid connected back in 2011, and our 2 megawatt unit, which was grid connected in 2016. We are headquartered in the north of Scotland, in some islands called the Orkneys, which see some of the world's strongest tidal stream currents. So a very good proving ground for our technology. Very recently, we actually secured a strategic investment from oil and gas major contractor Technip FMC in an endeavor and an investment to help us commercialize and deliver our technology at cost to a global market. So a very unique looking piece of technology, as I said, floating. What you see in front of you is the design for what we call the O2 tidal turbine. So it is moored and anchored on site, a floating platform, very much like a boat, beneath which we have two legs that have two drivetrains. These legs are hinged and articulated, can be driven by a hydraulic system to bring it up to the surface so that we have low-cost access to all major components. Our understanding about refining this technology has come from 20 years of experience and understanding that not only do we need to minimize construction cost and risk, but we need to make sure that you can access turbines as quickly as possible and as cheaply as possible, so you can maintain high generator availability and reduce operational costs. So you can see in the bottom images here with both the legs down in the operational mode and up in the service mode. And as I said, the whole platform is kept on station with large anchors, and the electricity is exported via a dynamic cable that comes out the bottom of the turbine onto the seabed and back to shore. Hopefully this animation buffers appropriately. So this is an animation of how the technology actually works. So we have pitching hubs that control the blades to make it capture the best amount of energy in both directions. And as you'll see here, a hydraulic system that drives a linkage that can bring the legs up to the surface. The power generating nacelles at the ends of the legs have access hatches that allow technicians to get access into those nacelles whilst the turbine stays on site. And this is what it looks like in real life. So this is the O2 tidal turbine. The manufacture of it is very analogous to shipbuilding. So we anticipate this as an industrial endeavor that will be able to put a lot of work and a lot of value through shipyards using existing technologies, existing supply chain, and existing know-how in terms of manufacturing. All the systems have been modularized to make sure that it's cheap and efficient to manufacture at volume. But as you can see at scale, it's a significant structure. The O2 is 74 meters long. We are using existing know-how as well in tidal stream energy. The challenge of extracting kinetic energy from flowing energy is understood, and it's very much transferred across from wind energy. So we use very similar composite material structures to manufacture blades, but indeed we actually use very similar pitch control methodologies to help us optimize the extraction of energy from the tidal stream currents. So as I said, the entire O2 structure, which is the world's most powerful tidal turbine, is of significant scale. So this is it built. We have about a 74-meter long superstructure that floats on the surface. And this houses all the major power conversion equipment. So the electric drives, the transformer, the control system. This is all very readily accessible with low-cost vessels. And it has a wingspan, for want of a better word, of over 50 meters. It weighs approximately 680 tons. It is a utility scale tidal turbine, although as I've highlighted, our concept is scalable. We have small turbines before for grid connection, but we are focused at this stage on utility scale application. So this current machine has just over 2 megawatt rated capacity, and we're looking at evolving this technology into slightly more powerful turbines towards the 3 megawatt area. Once it's in the water, it's very readily towable with low-cost vessels. So with the legs up, it has a very low draft, so it can be towed in a lot of different coastal areas. It only has 2 meters of draft, water clearance required, and we can use very readily available work vessels to tow the machine from where it's launched to where it's installed. So in this instance, this was a tow that was over 200 miles, very simply undertaken with low cost and done in less than 2 days. And this is it installed on its moorings in the north of Orkney. So a big tidal site here. Prior to the machine getting on site, we install the anchors and the chains and the cables. Very straightforward, understood operations, again, using low-cost vessels to be able to install the anchors and the chains. And then the machine can simply be towed on site, again with low-cost vessels, and it has the capability of installing itself onto its mooring connectors. The dynamic cable drops down to the seabed, is connected to a static cable, which takes our electricity back to the shore substation here in Orkney, which is only 1 kilometre away. Interestingly, in this project, we have battery storage to enable storage of the system, electricity from the system to feed demand when it's required, getting akin to baseload. And we actually have an electrolyzer as well to generate hydrogen. Zip legs down, operating up at 2 megawatts. Very simple, safe structure to get access to and do maintenance on. We have extensive environmental monitoring associated with this technology that we have continued from previous programs. And all recordings and data that we've recorded at this stage and analyzed indicate very low benign environmental impact of this technology. And indeed, it has a very low visual impact as well. We have very low rotor speeds, actually. Just for reference, we have a 20-meter rotor diameter on each of the drivetrains on this machine. So that gives it over 630 square meters of swept area, which is the largest swept area ever seen on a tidal turbine. But our rotor revolutions are less than 12 meters, 12 RPM. This is it in the water with the legs up, so you can see the configuration required for service and maintenance intervention. So I think I've actually hopefully kept the time. I might even have recovered time. I hope that's been interesting for everybody to have a view of the technology that we've developed here. As I said, it's a leading technology. The O2 is up and operational. It is a commercially funded turbine. As I said, we recently secured a strategic investment from an oil and gas service major that is focused on commercializing and deploying this technology at cost around the world. And we are very interested in exploring opportunities that we see of being able to deploy this at utility scale within the Indonesian region. So I think that probably will do me. Thank you very much.
Thank you very much, Mr. Andrew. This is a very big unit in tidal. I think this is one of the biggest, 2 megawatt, right? That's quite big. Usually the size is about 250 kilometer or 1 megawatt. This is 2 megawatt. I think it's interesting. And for you that have question, please type on the chat, or we can have at the end of the session. So we move to the last speaker of this session, Mr. Simon Forrest. Are you here, sir? Already?
Yes, I am.
Oh, thank you. Thank you very much. Mr. Simon Forrest, he is Chief Executive Officer of Nova Innovation, and he has experience like in this screen, in Nova Innovation and also Wood Mackenzie, University of Edinburgh. This is I think it's a lot of experience here, and his background is in electrical and electronic engineering. He is presenting technology on Nova innovation. Please, the time is yours, Mr. Please.
Thank you very much, Professor McTassa, and good afternoon, everyone.
Good afternoon.
I just check. My name is Simon. My name is Simon Forrest. I am CEO of Nova Innovation. We are a tidal energy company. We are based in Scotland, but also have offices in Canada and soon opening one in Indonesia as well. The slide you see before you is effectively a picture of what we do. We design, build and operate underwater wind turbines. They are tidal turbines that sit on the seabed and produce clean, predictable electricity. Some of our background on Nova. Nova Innovation was the first, deployed the world's first offshore tidal array in 2016, and that was in the Shetland Islands in the north of Scotland. We have a 0.5 megawatt array up there, and it has been successfully powering the homes, businesses and the Shetland grid for over 5 years. In 2018, we combined our technology with Tesla energy storage, and we have been producing baseload tidal power for the Shetland Islands since 2018, and these are islands of 22,000 people. In 2020, we won our first international contract, and we are actually installing and building at the moment the first installation of our turbines in North America and Canada, and that will be a 1.5 megawatt project with 15 turbines over the next 18 months. In terms of the challenge that we are facing, everyone on this call will know it is the climate emergency. We need new forms of renewables, not just solar and wind. With solar and wind, sometimes the sun doesn't shine, the wind doesn't blow, but tidal energy gives clean, predictable energy that we can predict years in advance. And here's part of the solution. This is actually an image, a picture of our tidal farm up in Shetland in the north of Scotland. Spot the tidal power station, you don't see it. It all sits subsea and it has been producing clean, predictable energy for the islands for over 5 years with no visual impact, no navigational hazard. It's been unaffected by storms, and we've had some of the worst storms in history have gone through Shetland in the last 5 years. And we also have a wealth of environmental data. We have been analysing the site for over 10 years and have live data for 5 years that we have shared with the regulator. And the regulator has now verified that there's no negative impact from our technology. And this is.
Do you have something to share with us on screen?
Is that not sharing? No. Let me go back. Sorry, I thought that was sharing. Can you see now?
Oh, okay.
Can you see the screen?
Yes, 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 good now. Yeah.
Okay, right. I thought you could see the screen that I was showing. The marine energy. This is basically a picture of our turbines. It sits subsea, produces clean, predictable electricity. In summary, this is really our business. We produce these underwater turbines. As I said, we delivered the world's first offshore tidal array in 2016, and it's been generating electricity for the Shetland grid, homes and businesses for over 5 years. The turbine sits on the seabed with a cable back to shore and is connected straight into the grid. It is built for rapid deployment, low cost. We use very small local vessels. And it's scalable from 100 kilowatts up to multi-megawatt arrays. In terms of the market opportunity, I mean, it's a truly global opportunity. It's a massive, abundant, untapped market. And we're currently working in North America, in Europe, and are working in Indonesia, have been working in Indonesia for the last 3 years, looking at sites. In terms of our current portfolio, we have 3 projects in Scotland, 2 in Wales, We're working in Canada and deploying at the moment. We're also working in Indonesia, and indeed we're working with Professor Muktasa's team looking at feasibility study of projects in Indonesia. In particular, we're looking at the Larantuka Strait, 7 megawatt, and looking at the feasibility and the financial case for that. As I say, we have someone on the ground in Indonesia and have been working there for the last 2 or 3 years. And these are really the systems that we install. We are known for tidal energy. That is our core business. But in Shetland, we have also installed energy storage with the Tesla battery. We have put in a private wire to the local ice house to serve aquaculture and the fishing industry. And we have combined it. We have now put in electric vehicle charging points. So it's not just about tidal energy. This is an energy solution that meets the client needs, particularly when we're going to islands where energy is perhaps expensive because of diesel generation, as it is in Shetland, but also it's to help the economy of the island. In Shetland, fish is king. So, and really everything in terms of the economy is geared around that with some oil and gas. The other thing to notice on here as well is that we are now combining our technology and our smart grid systems with hydrogen and other forms of renewables. Indeed, in Indonesia, we are also looking at building hybrid systems, not just tidal, but looking at floating solar combined with energy storage so that we deliver a solution that meets the client needs. And as you can see, a heat map in terms of solar resource for floating solar in Indonesia is just astounding. Indonesia is blessed with both solar and tidal resource. And we believe Indonesia will be the biggest tidal energy market in the world. Finally, I've got a short video, just 60 seconds, just to show you and give an impression of the systems we have been installing and running in Shetland for the last 5 years. So hopefully this video will work. That is our operational tidal turbine. It's worth just reflecting on that short video because I think it shows you just how quickly things can change. In the Shetland Islands, we now have cars driving up and down that are entirely powered by the tide. And that shows you how quickly technology can change, not just our energy systems, but the way we live our lives in islands across the world. And finally, just a word on our UN Sustainable Development Goals. Of the 17 UN SDGs, we impact 6 directly and 9 indirectly. And we have an impact across a wide part of society. What this does is this helps accelerate funding, not just from World Bank and Asian development banks, but now from private investment as well. Thank you very much.
Thank you very much, Mr. Simon. It's very interesting technology. So, ladies and gentlemen, we have time now for question and answer. Please raise your hand if you have a question directly, or you can also type in the chat room. This is a question in the chat room that let me share together. This is for Dr. Anna. Let me share screen. Oh, sorry. Let me share screen. Where is the question now? This is in chat screen. I'm sorry. This is first one is to Dr. Anna. What is the question? Why ocean energy is the least developed renewable energy? And also the question regarding capacity factor for Keong Hong, for Dr. Keong Hong, capacity factor for tidal and wave. And also there is a question for Mr. Scott. Please directly, first one to Dr. Anna. Please, Dr. Anna.
So why ocean energy is the least developed, the renewable energy? Ocean energy is approaching commercialization. So we see the deployment of full-scale devices in real sea conditions. We saw these projects from Nova Innovation and Orbital Marine Energies. These are very good examples of the success in this sector. However, I would say to be very simple in my answer, I think it's a question of level of funding. You need to go to the water, to real sea conditions. You need appropriate level of funding. You need to go with a robust technology to survive in extreme sea waves. And this is very expensive. So it's a question of appropriate level of funding in this sector. Public funding that will attract public investment. In a clear way, that's what is missing. Compared with offshore wind, for instance. Wind, there is a long history on the development of wind energy inland, which is more easy than in the operational environment at the sea. So at offshore wind at the sea is taking the experience of a long development path on the wind inland. Ocean energy is doing this, is also doing this progress. There is a continuous flow of new ideas and new concepts which in a way it also disperses the funding, because if there was a convergence for a single technology, the funding will be allocated for the development of this single technology, but it's not what we have seen in this sector. So there is here a problem of no lack of convergence, dispersing the funding for many different concepts, and still a lack of appropriate funding level. However, the Ocean Energy Europe, European Association on Ocean Energy, is doing a lot of work on bringing the right level of funding for this sector. I would like to make this note as well. And organizations like IEA-OES are also calling the attention for governments the need to continuously give public funding to this to the development of ocean energy.
Okay. Second question is for Dr. Keong Hong regarding capacity factor for tidal and wave technology, and also this is a question regarding wave energy converter. There are two typically almost opposite design target for PTO. So please, Dr. Keong Hong.
Yeah, firstly, the capacity factor. I think actually I'm the expert in wave energy converters, so probably some other speakers from tidal energy device developer can answer tidal energy device for the capacity factor. For the wave energy converters, you have many different types of wave energy converters. So you cannot say just one capacity factors, but there are many key parameters deciding capacity factor, and probably target for the wave energy converter is something like 20% or 25%. But there is a large variation because, for example, OWC devices, you have about 20% of energy conversion efficiency. That's kind of the important factor. But some other devices like oscillating body types or point observer, conversion efficiency is like 50%. So it's a big difference between different types to types. Also uncertainty there because no devices until now has a long field operation. We don't have much data for it. So there is still many uncertainties, but in my opinion, eventual target is very close to the tidal energy device or wind energy, wind turbine devices. So probably little less than that means 20 or 25%. We have much more fluctuations. So ratio between the average power to the rated power is a little lower than other devices like a tidal device or wind turbines. So my opinion, 20 or 25%. Can somebody answer the tidal current devices? In my knowledge, it's similar to the wind turbine devices, like a 30% or 35%.
That is correct. Our turbines in Shetland, our latest turbines.
Dr. Keong, there is one more question regarding, this is from Pak Ali Mudakir, integration between wave energy and breakwater. Which island is that? Where?
It's a Chuja Island. It's between mainland and Jeju Island. It's 1 hour distance by past the ship. So it's about 8 kilometer, 60 to 70 kilometer away from the mainland, and about 2,000 people residents in that Chuja Island. So it was constructed in Chuja Island.
Okay, thank you. And then now there is a question for Mr. Andrew Scott. Please, you can also hear there's a question regarding report on tidal power that had been released. The question is the relation between power output and the structure, and also the dimension of the equipment or something like that. Please, Mr. Andrew.
Yeah, certainly. So obviously our structure serves a number of different functions, but primarily one of the biggest ones is buoyancy, to float the entire thing. So as the technology as you scale it up, obviously the masses become larger, so the structure has to have more buoyancy in it. And indeed, it's got to be able to provide reactionary force for the thrust loads coming on. And so just to give you an idea, 2 megawatts of power generation, we can be dealing with cumulative thrust loads that translate into about 140 tons of mooring load. So that's one of the main drivers on the overall top structure, whole structure is buoyancy required to kind of accommodate that. And the other part of the structure really probably is the main part is the legs that obviously house the powertrains at the end of them. So their length, the scale of them other than strength to take the thrust loads, but they also have to be the right length to position the rotors in the water column in the right place. So we make an allowance on the top side in terms of tip to surface distance, and we also need to make an allowance on the bottom side. Crucially, of course, with floating tidal, your reference is the sea surface rather than the seabed. And as we all know, from a shear effect and turbulence effect, is that the best resource of tidal streaming is near the surface. So the overall leg structure and the floating approach allows us to position the rotors in the fastest part of the flowing tidal currents. Hopefully that helps.
Thank you. And then the last one is to Mr. Simon. Please, Mr. Simon, a few chat for you. This one regarding, for example, the dimension of the equipment, cut-in speed, and also some other detail here. Please, Dr. Please, Mr. Simon.
Yes, thank you. Our turbine sits on the seabed, and the hub height for the turbine is 8.5 meters. That leaves plenty of draft clearance, and we have deployed our turbines in very busy shipping channels, and they just go right over the top. In terms of the cut-in speed is 0.8 meters a second, 0.8 meters a second, and we can go in to tidal streams up to 10 knots.
How about the cut-in speed?
0.8 meters per second cut-in speed.
0.8, yeah?
About one and a half knots. One and a half knots.
Yeah. This is a question also from Dr. Sony from PT Teradaya to Mr. Simon and also Mr. Andrew. He said about the condition or the environment of marine energy in Indonesia quite different from Europe. Is there any comment on that? And also, is there any information that can be studied related to your equipment to the environment in Indonesia, for example, something like that? From Pak Sony, please, Mr. Simon, please.
Yep, he is absolutely correct. It is. There are different environments that we are putting these in, but many of the things are similar in terms of the seabed bathymetry. There is a wealth of information about projects and our own project in Northwest Europe. If you visit our website, you will find all these environmental reports, independent regulator reports, and links to them. So that information is there. We are already looking at the environmental aspects of projects in Indonesia. The good thing is, although they are different, we are not starting at the bottom level where we did 10 years ago in Scotland. So we already have some of the models that we can use, the types of surveys that we want to use. So that information is there, and we are now building up not just a knowledge base in Europe, but a knowledge base worldwide on the environmental aspects of the sector.
Oh, thank you. Please, Mr. Simon, Mr. Andrew, I'm sorry. Please.
I don't think I'd add very much to what Simon was saying there, other than, obviously what the other very similar features, tidal currents themselves are pretty much the same. So, one of the other areas that is important to try and start to map is the resource itself. So, the performance and the yield of a project will be very, very closely related to the speed profile of the currents that you have on a site. So it's very important at early stage to try and build up a better picture or a clearer picture as to the types of currents that you experience on your sites, and you start to map that resource, because that can translate directly through to yield calculations, which is set against against a power curve as Simon said, it's exactly the same as wind. We have a cut-in speed with our turbines, and then we have a rated speed. And it's fairly straightforward to map that power curve across a speed profile to understand what a project's yield will be. And these are something that technology companies are quite happy to work with you with. But speed profile is a really important one to characterize at an early stage.
Okay, thank you very much. Now exactly 3:05, and this is the last of our session. I'm sorry, I'm so sorry that our time is so limited. This is because the material is so much and the topic is very interesting. So maybe many questions from you that had not been answered. Maybe you can, our audience can contact the committee, and if any question, we can deliver contact to the presenter. And also, if presenter have material can be distributed, committee of this conference will help to the participant to have the material. So thank you very much for this session, and we break for 10 minutes, and then we will start to the second session. So thank you very much to Dr. Anna. Thank you very much to Dr. Keong Hong. Thank you very much to Mr. Andrew Scott. Thank you very much to Mr. Simon Forrest. Thank you, and we see you in the second section.
Thank you very much.
Okay, everyone, please come back in the room again. Okay, thank you. Good afternoon, ladies and gentlemen. Welcome back to the Ocean Energy session. Indonesia EBTKE CONEX is an integrated event dedicated to drive the growth and development of sustainable energy in Indonesia. I'm Dendi Satrio as the co-chair in this second plenary session. In this session, there will be 5 speakers with 15 minutes presentation each. Then in the last, there will be a panel discussion or Q&A session. Okay, ladies and gentlemen, let's start the first session or the first speaker. I will share the curriculum vitae. Our first speaker is Dr. Ahmad Firdaus from PT SBS Indonesia. He has several experiences, such as involved in many research projects on marine renewable energy, and also involved in many port development and design projects. His background is a Doctor of Philosophy from University of Oxford, and this afternoon he will deliver presentation about prospects of ocean current development in Indonesia. Dr. Ahmad Mukhlis, are you ready?
Yes. Can I share my screen now?
Okay, please. Thank you.
Okay. Thank you very much. Good afternoon, everyone. I'm from SBS. I'm going to, as been requested by committee, so I'm going to present the presentation with the title of the prospect of ocean current development in Indonesia. So basically, the material from this presentation has come from my previous experiences on research and development on the tidal currents technologies. So we're going to explore more, and then looking forward for the opportunities of tidal currents development in Indonesia. Okay, so this is the outline of the presentations. I'm going to talk about the tidal technologies, the tidal turbine technologies, and about the opportunity of renewable energy in Indonesia. So we talked a little bit about the rules and the regulations, laws and the regulations in this country, whether it has opportunity for renewables and everything. And we also going to do to look the specific case, like such as Larantuka, and then look for other challenges actually. And then this is the device concept. So this is what I've been in contact with this technology. So while I'm in Oxford, so it's actually, although it's not on my research group, it's actually sources, but we quite close to each other. So I get the updates. So one of it is developed by my supervisor, the Kepler turbines here, and also this one. This is the latest one. Is been developed by another professor in the University of Oxford. And then this one, so I'm going to talk a little bit more about this one. So this one is the technology that I've been developed since my master degree in ITD. Yeah, I'll explore more about the development of this technology. So this is the idea. The first idea is actually we developed the cross-flow type turbines, and then some. I think it's in 2011. So the Marine Research Agency under the Ministry of Ocean Affairs and Ocean and Marine Affairs in Ministry interested with my idea actually at the time, because it's the one that's developed from my master thesis. So they funded the idea to develop the prototypes. So this is the prototype. So we test the prototype at the the channel on the coal-fired power plants. So this is quite interesting. We tried renewable energy on the coal-fired power plant channel, exhaust channel, and this is what we got. So see, we test that. We have a lot of data from this, but we found out that it's hard to do that on this kind of channel because our turbine being hit by some debris or some rubbish that goes to that channels. Yeah, it's only lasting for I think it's for 20 days before it's stuck by a very big mattress, bed mattress, and then it's broken. And then we move back and try to look for another facility. So we have collaborations with the hydrodynamic laboratory at ITS. It's actually under the BPPT at the time. And we did the testing, the laboratory testing with the prototype scale of turbines in that facility. So this is the facility that we use, and then this is the turbines. We developed the idea from the beginning because my idea is actually how we can have the turbines without any spherical shapes. That is really hard to develop. And then this is the turbine, and we test. We get some potential from there. So this is the testings from the towing time of that laboratory, and then we also did the field testing as well at the Suramadu Bridge. So this is the testing. But to be honest, this research has been stopped since I went to Oxford. So I went to Oxford in 2016. So this is the last project that I involved for the development of the turbines. But we already have this one. But the main issues of these turbines will be in the reliability. So I think it's just most of the cross-flow turbine encounter the same issues actually. So we have the same problem with this one. Okay, let's move on with the opportunity. So this is based on my doctoral research actually. So in the beginning we can find that I remember that when at 2019 when the re-election of when the presidential re-election campaigns began, many people in this field said that the Jokowi administration is not keen to the renewable energy. So although by the presidential regulations in 2014, we can see that the growth of the renewable energy is just projected to should be increased in 2025 to 23%. But based on this calculations, the demand of electricity of Indonesia is indeed will be increased in following years, and then if we see that by the capacities will be the needs of Indonesian's electricity will be 60 gigawatt. So it's like equivalent to 175 million ton of oil equivalent or MTOE to 430 gigawatt in 2050. So this is a lot of energy needs for Indonesia. And as I mentioned before, in 2025, presidential regulations targeted to 23% of renewables into it. So we have to see these plans is going forward. But a lot of people feel like, yeah, it's going nowhere since at the last re-election campaigns, a lot of people argue that whether Indonesia goes to this toward the green 20% of its energy mix from the renewable energy. And okay, so I have this explanation. So when I try to look for the data, so I try to look the data from the 2014. Okay, let's see this electrification ratio at 2014. We got this electrification ratio. So actually, our nationwide the electrification ratio in Indonesia is around 88% at the time. So it's actually is around 30 million of Indonesian population doesn't have access to this modern form of energy. Yeah. So you can imagine this 30 million is a lot. It's almost half of the UK populations. And so looking to the 2019 electrification ratio is rise up to the 98%. So it's actually a remarkable achievement. Actually, I can say, okay, so we can understand that at the first term of his administration, he must be focusing on to give access to electricity to all Indonesian citizens. Although, as you see, that is by the distributions of the electrification ratio. And so, for you is not familiar with the electrification ratio. Electrification ratio is the percentage of the people can access to the electricity, or the population can access to the electricity. So increasing from 88 to 98 is remarkable achievement actually. So we can understand the first term of his administration is just focusing on to equalize the access to electricity. So we can understand that. So we can say that Indonesia still have opportunity to develop for the renewable energy enthusiasts should be have what I call this the opportunity to development of the renewable energy is still high in this regard actually. Okay, so this is the what you see in your screen is actually NOAA night lights maps in Indonesia. So what we see here, as you see, so only Java Islands has light tone here. So you can see that the night light is not just indicate the access to electricity, but also indicates how reliable the electricity in those areas. Because this one is this exposure for 1 year or annual productivity electricity in this particular area. So as you see, so only Java Islands has bright lights in this regions. So that means we can say that in the eastern part of Indonesia, maybe they do have access to electricity, but it's not so reliable. So this is another homework for us actually. Okay, so let's see the tidal energy potentials for Indonesia. So this is based on the associations, Indonesian Ocean Energy Association, which is I involved in developing these maps before. So we assess 10 potential locations in this area. So what we got here, so we actually this map has been developed, but it's not been updated yet. But I believe there's a lot of government agency has already done some resource assessments, some measurements, observations in the fields, and showing that the increasing number of the potential locations of Indonesia. Okay, this is my research actually in Oxford, doing so actually my main research is doing the investigation of the characteristics of tidal energy in Indonesia. So it's specifically in the location like in Indonesia, because Indonesia is quite different as in the northern hemisphere, such as Europe and Canada, because those area is mainly semi-diurnal. In Indonesia, we have diurnal, strong diurnal components in this location, so that this locations has more complex tidal pattern, which creates more complexity in the development, and the plans, and in the assessment and everything. So it's so I hope and I believe my research can be a breakthrough to the development of tidal resources in Indonesia in the future, because I have a lot of findings regarding the tidal resource characteristics in Indonesian's water. Okay.
Pak Ahmad, I'm sorry, 3 minutes more.
Okay, sorry. Yeah, so this is the resource calculation that we use. We use the Hospi-Whelan models. So maybe later on I can explore more. And I think I skipped some of the slides here because I have a lot of important slides. So this is the sum of the resource that I've been assessed in this location. So yeah, what we did actually, we are develop a method to do the resource assessments that considered the realistic turbines in the theory actually. So we push the theory further, and then we can assess the electricity resources in certain area based on the characteristic of the turbines, the specific turbines. And then so this is the we also implement the rated power, which is we could implement the thrust capping and power capping, and I can answer you in detail if you interested in this. And then so we also calculate the capacity factors, capacity factors of the resources, and I calculate so we also introduced the new capping metrics for the tidal resource like this. So we introduced the power factor, thrust factor. This is the maximum thrust and power factor. So we know that the difference between the when the turbines between the resource that are available in particular locations, and the thrust factor. And the resource that will be produced by certain technologies in certain area. Okay, since this is the example of the implementations of the capping strategy, so this includes the power capping strategy that's applied in certain turbines. So we know that the turbine capacity that will be good enough to install in certain area. So this is the calculations. So based on the B14s, 14 meter diameter with the space between turbines, the tip to tip space is 14 meters, and then the number of stacking is 1, and we got the calculations. And also based on the information that I got from the websites, and then the calculations of the LCOE can be done in this certain area. So as you see here, if the technology in this certain area could achieve that low cost of low capex as I mean in the range of capex that's available in the UK markets. So it's like usually in the UK, the estimated capital cost is between 1,400 pounds sterling per kilowatt capacity. This one is 3,000 kilowatt pounds sterling per kilowatt capacity. And then we can calculate the LCOE based on that, just based on those range of numbers. So we know that in this area we can have around let's say this one is of 10 cents US dollar per kilowatt hour to 20 cents per kilowatt hour per US dollar per kilowatt hour. So that means this area will be lucrative for tidal energy compressions. Okay, so I did the financial analysis as well. So looking for the in which
Dr.
price.
Ahmad?
Yes.
I'm sorry, the time is up. Maybe you can.
Okay. Yes. So I jumped to the conclusions. Actually, the conclusions is Indonesia has great potential of tidal stream energy, and the assessment also found that some sites are economically viable for the commercial turbines developer based on the current status in the UK markets actually. But we have to admit that government interventions for intervention in regulatory aspect such as tariff regimes might be essential for the materializations of tidal energy investment in Indonesia. Okay, that's all. Thank you very much.
Thank you, Dr. Ahmad Firdaus. I'm so sorry because the time is very tight.
Okay.
You have a lot of material, but there is only 15 minutes to present. So we continue to the next speaker. The next speaker is Mr. Ian Johnston. He is a director of Aquaterra. He has several experiences, such as director in Aquaterra, transport manager in the OPNE aggregates, and self-employed trainer in the freelancer technical trainer, and so on. This afternoon, he will explain about strategic planning for the blue energy contribution to total energy transition. Okay, Mr. Ian, the time is yours.
Thank you. I'll just share my screen if I can. Okay, hopefully you can see my screen now, and we can carry on. So my presentation will give a kind of overview of our opinion of how Indonesia can meet the energy transition that it requires, and the work that was done at the recent COP meetings, where the Indonesian government committed to this energy transition. And Aquaterra, the company, has been working in Indonesia for the last 10 years, and we have done an awful lot of resource assessment and resource planning within Indonesia. And the presentation I'll give is just some of the details of where we are. We have a lot more detail. So this slide here, I'll not go through the lines in detail, but I was quite pleased that it actually matches in with our previous speaker's research, I think, and the numbers on a quick calculation are very similar. And you can see, and I'm sure a lot of people on in the conference will understand the huge demands there are for energy in Indonesia, but equally the scale of the amount of renewable energy that would be required to meet that energy transition to a low carbon future, which we are all in the world need to be committed to. And as I said earlier, the Indonesian government has committed to over the last few weeks. And so the key point, I think, of what we're all discussing today, and the previous speakers have given us outlines on it, are: can blue energy options contribute to that transition? But there are a number of questions, and some of these questions have been highlighted in previous presentations. Is where's the best place to do it? What is the right technology? How are we going to deploy that? And what, particular, at what price? So again, as has been highlighted as previous speakers, and the reason that we're probably all here today is that Indonesia has tremendous renewable resource. Obviously, solar, as you all know, compared to my position in Scotland and Orkney, where today it's 3 degrees, the solar resource in Indonesia is absolutely tremendous. You have very strong wave resource, wind in certain areas, geothermal, aquathermal, and hydropower. So this slide is a distillation of some of the work we've done over the years, and a lot of the small dots you can see there. We are particularly renowned for our resource assessment and understanding the tidal energy opportunities within Indonesia. All the small dots you're seeing on this slide give an indication of where we think there are tidal potential, which is probably slightly more than the previous speaker. But and I think it was highlighted by Simon Forrest in one of the previous speeches, that each one of these resources needs to be linked together. So the opportunities to link that to storage and to the whole energy system is what we've been looking at in particular. So just to give an indication, and people will have seen this before, the wind speed data across Indonesia. Now you can see here there's some extremely strong areas of wind speed. So offshore wind has a huge potential in Indonesia, not unrealized yet, but there are some areas in this area, the green areas, where there isn't much wind potential. So the potential of the different technologies needs to be matched to where the resource is. Some of the work we've done looking at wind, these are the sort of areas, and again, I'm not going to talk through this, just given that we are need to keep to time, but these are the areas where we see some tremendous potential for offshore wind. And you can see even within the 6 areas that we are highlighting in this table, there's a huge variation between south of Papua and Aceh, but there are potential across the place. Each of these areas will have a unique combination of different markets, resources, and attributes to be able to develop that. And in particular, as we briefly mentioned with the last speaker, some of the interconnection issues in Indonesia are a real challenge to make sure that the whole of Indonesia is connected. So it's not just about resources, it's about the needs of the areas. It's about what other alternatives are there, what you can link with. Some of places it's acceptability of development. Indonesia sits with a lot of biodiversity, and whatever we do must be linked and must be environmentally acceptable. And then there's a cost element to it. And then is there other developments that can be linked alongside industrial or strategic opportunities? So one of the areas that you need to link to is, and this kind of highlights similar to what the previous speaker had on his nighttime map, shows some of the industrial and urban centers across Indonesia, and you can see the concentration around Java, but there still are some huge potential areas of industrial potential across Indonesia. Again, looking at connectivity, where the power stations are at the moment, and this is a map showing the different power stations across Indonesia where there will be grid connectivity. So that's a good place to start if you're looking at developing renewable energy projects. And then this is some work we've done looking at markets, and the markets vary a lot across Indonesia, and this actually market map is the same across the world, really, on where you look at the slightly lower value markets that maybe are high volume, low value, so grid connected projects that are looking at that grid price for electricity, which can very often be the lowest price of electricity, and then moving up into the very small niche markets that was mentioned earlier, about where you might make higher value projects. They don't need to be nearly so big to give the same commercial return, but they very particularly fit in with a detailed market. So we've seen some of these technologies already on the tidal side, and they're very different, as you saw from Simon Forrest and from Andrew Scott with the orbital devices. So matching the device to the resource is important, linking it. So we see great potential for floating solar across the place. Again, if you look in the top left-hand corner of this slide, you're looking at navigational elements, very niche markets, very high value, very difficult to get grid connected. So a solar option is absolutely ideal for there compared to the bottom right market, where you could have a fairly industrial size of solar project that can make the program work. And then another thing Indonesia needs to seriously think about is export markets. You know, this is just one example across Indonesia where if you're successful and we can make renewable energy work successfully in Indonesia, there is a potential to export across to some other areas where energy is highly valued. So this is again some of the work we've done where across Indonesia, where we're trying to look at the connectivity of the whole project, and one idea across the region where you can see in this indication that there is wind, solar, tide, and other potentials that could be linked together, and the possibility of a trans-Indonesian subsea cable just to improve that connectivity across the whole place. So, in conclusion, really, we do see there's huge potential for blue energy to help with the energy transition. These are some of our broad-based estimates and some of the site-specific estimates of what we could do. But we think blue energy has a potential for somewhere around 1,230 gigawatts, mostly floating solar, we feel at the moment, but blue energy can make a huge difference to Indonesia's energy transition. Thank you.
Okay, thank you, Mr. Ian. Very nice presentation because specific in Indonesia the case. And I will remind for the participant who want to discuss or asking a question, please give the question via chat box, then we will select and deliver to the speakers at the end of the session. Okay, let's continue to the next speakers. The next speaker is Mr. Jonas Kampf. He has several experiences, such as Chief Executive Officer at Wave4Power from Sweden, and Chief Marketing Officer in the Blue Orbis, and Commercial Director at PT Subsea, and the others. Very much experience. And now he is as a Chief Executive Officer, CEO of Wave4Power from Sweden. He will deliver material about ocean as future Indonesia strategic energy resources. Okay, Mr. Jonas, please, the time is yours.
Thank you. Thank you very much. I will share my screen with you and show a presentation.
Yes, please.
You can see my screen now?
Okay, 990.
Yeah, you can see, I hope you can see the screen now. So, this is what we really are going to talk about today. Do you know what this is? 990. It's the all-important number when it comes to marine energy. How can that be possible? Well, every day, the ocean waves of the world are charged with at least 990 times more sustainable energy than our world requires. It's free and it's green. The question is how to harvest this energy. How can we take care of all this energy in a good way? Well, here is one answer. Well, actually, here is the answer. And it looks like this, live from the Norwegian coast. This is the Wave4Power Wave L system, generating electricity, delivering it to the Norwegian power grid. We have a proven concept of 12,000 hours in the North Atlantic with 4,000 hours delivering electricity to the local grid. We have 940 million measuring points of data from this proof of concept. We can deliver up to 500 megawatt hours per buoy in a year, which means that we will prevent up to 500 tons of CO2 emissions per year per buoy compared to burning fossil fuel. If you look at wave power, it's very consistent, it's predictable and available 24/7. This is a comparison made in the United States, and they have several weeks. I've just picked 1 week. The yellow shows the sun, the gray shows the wind, and the black line shows the consistency of the wave energy over time. And this is quite interesting because it's very close to a base load solution. If you combine it with energy storage, or you can make a combination of, for instance, wind, solar, and waves, you will have a very good energy system. If you look at the energy content in wind, for instance, the wind energy content increases when you get away from the surface. The higher up you get, the more energy there is in the wind. But if you look at waves, the energy content increases closer to the surface. This is the big challenge in wave power, is to survive in this climate and be able to harvest the electricity. That's why we have built a concept from our wave system. First of all, survivability. We need to be able to survive. We will move with the wave, not against them. With an elastic, flexible mooring system, we have to have serviceability. We have to have access to the system from the surface. We don't want to have access with diving operations and subsea operations. It's too costly. So we have to have access from the surface with a high modularity, so we just can replace parts if they break. And a high degree of standard components combined with patented details. And then, of course, profitability for everyone involved, including the environment. This is a very environment-friendly solution. No harm to the bottom environment. We have proved so far that we have faced 14-meter high waves at the test site in Norway, and the system is optimized to take 25-meter high waves. So Waves of Power it's a Swedish corporation incorporated in 2012. The Wavell system has an economic lifetime of 25 years. And for a park owner, the return on investment per year would be somewhere between 12 and 16%. Ideal water depth is between 50 and 300 meters, with a wave period of 3 to 9 seconds between each wave. Installed power per buoy is 250 kilowatts. And we are also going for a global marine classification by DNV in 2022. Revenue model very straightforward, either turnkey systems or power purchase agreements. And then, of course, service and maintenance contracts. If you look at the Wavell Park, the buoys are placed in clusters of 6 buoys and 1 connection hub in each cluster. And these are linked together in a pre-designed pattern in order to work in the absolute best possible way. As you can see here, you can see how it's linked together, but this is what is visible at the surface. So it's high degree of invisibility if you stand on shore and look out over the horizon. So this can be a large park can consist of thousands of buoys. We're working with world-class industrial partners, many on whom you recognize: Siemens, Petronas, Borealis, NKT Cables, etc. And this is what has brought us so far as where we are today. Because with us, we have a tremendous development organization available in those companies, and also a lot of well-tested standard components that we can take from the shop. We have a very strong focus on reducing the levelized cost of electricity. And you know, that is the kilowatt cost during the system life. And if you look at our expected development curve, it looks like this. We're starting at somewhere around 15 cents, US cents today in the first systems, and we are aiming to go at a low 3 cents as volume increases. We will achieve this by following the economy of scale development. and we aim to be on par with land-based wind in 3 to 5 years. We offer a safe supply of energy, and a very commonly used parameter in the business is installed power per unit of weight, if you look at marine energy, kilowatt per kilo and per year. And today, the Wavell system is somewhere between 8 to 10 kilowatt hours per kilo. That is among the highest figures in the industry. The world offers great wave climate for wave power, measured in kilowatt per meter of wavefront. Just to give you one example, from the US West Coast, 1% of the energy in the waves on the West Coast of the United States can supply 1/3 of the country's total electricity need without problem. But how is it in Indonesia? Well, Indonesia offers a great wave climate for wave power. As you can see, between 30 and 40 kilowatt per meter of wavefront is ideal for wave power. So you have an extremely good wave power resource to access in the sea. This is also a great business opportunity to convert old offshore platforms, oil and gas platforms, to H2 plants powered by wave power. You have the water to produce a hydrogen from the sea, and you have the electricity that is required to produce from the waves in the sea. It takes approximately 50 kilowatt hours to produce 1 kilo of hydrogen. 100 megawatt wave power can produce approximately 4,000 tons of hydrogen per year. And in the end, the only waste product is clean water. Our planned growth in Indonesia is that we are now taking part of this, what we call the Business Acceleration Program in Indonesia through Business Sweden. We are looking for local production partners, local marine operations partners in Indonesia, because we believe that a lot of to do business in Indonesia, I think it's very, very important to be local, to have a good local contact, and to operate in the society. And this is how we work all over the world. We're aiming to get the first contract in 2022, first pilot contract or whatever we call it, and then follow up with the next contract in 2023. And after that, we hopefully have a good growth with large-scale power contracts in Indonesia. So our mission is to make money by generating a better future for our planet. Our vision is a future where our children and grandchildren can live without fear of climate change, and power is available for everyone. This is what we call the green wave forward, the green wave forward by Waves for Power. My name is Jonas Kampf. I'm CEO of Waves for Power. I thank you very much for listening. Thank you. I'm looking forward to your questions later.
Okay, thank you very much, Mr. Jonas. Very nice presentation. I captured that one buoy can be produced 250 kilowatts. But
no, it's installed power of 250 kilowatts. That means that with a capacity of factor of slightly over 20%, we will produce 500 megawatt hours per year per
buoy. So if we have like a farming, there is several buoy, there is a lot of energy from.
Yes.
Okay, thank you. Okay, thank you, Mr. Jonas. We will continue to the next speakers. If the participant want to ask to Mr. Jonas, please deliver the question in the column chat first. Then I will deliver and read to the speaker in the last session. Okay, the next speaker is Dr. Zainal Arifin. He is a directorate of planning from PT PLN. PLN is a electricity utility company in Indonesia. He has several experiences, such as senior manager of engineering and procurement in PT PLN, then vice president of technology development in PT PLN also, and he is also senior lecturer at Institute Technology PLN, and now he is an executive vice president of engineering and technology in PT PLN. Dr. Zainal Arifin will be present about approach for new technology in the electricity industry, reference to the ocean energy development. So now, please present your material, Dr. Zainal.
Okay, thank you. Good afternoon, everyone. Allow me to share my presentation. I would like to share about not the ocean energy technology, but how we manage the technology for powering Indonesia. So I am from PLN, the electricity utility state company in Indonesia. So I would like to start with the who we are, already introduced by the moderator. Actually, PLN is one of the largest Indonesia state-owned company with more than 100 billion US asset and revenue about 19 billion a year. We are the largest electricity utility in the Southeast Asia. We have end-to-end business model of electricity for power generation until transmission, distribution, and retail. Right now, we have over 8 million customers. So we now already on the energy transition, and we know very well that the energy transition move us to more electrification in the future. The electricity will be the more central of energy carrier, but we should aware that more than 80% will come from the renewable energy. So why we welcome to the green technology. In Indonesia, for the next 4 years, based on the new Indonesia business planning, we should build at new renewable energy capacity at least 5 gigawatt, 5,000 megawatt in the next 4 years for achieving our target 23% fuel mix of renewable energy for electricity. So it's need a role of PLN as the only one utility company who have the end-to-end business model, who operate and own the grid. So because of that, so we should know how PLN do the technology selection, technology assessment for the powering Indonesian area. So actually, the technology orientation as utility company, we do not invent the technology. We only adapt and innovate, maybe incremental innovation. That's my position. We don't not create the technology. So we very welcoming you, all technology provider, to join with us to select the best technology for Indonesia, especially in this event, ocean energy. This the PLN technological characteristic, because we have end-to-end business model for the electricity utility. So we have the power generation, consists all thermal fossil fuel power plant, and also some renewable energy, transmission, distribution, supporting, and so on. We have several technologies there. For managing the technology, of course, we need some technology management. We call it technology management system. This regulate who person in charge, what technology should be used by the firm, whom the technology utilization partner with, how does the firm utilize the technology, and so on. So as utility company, PLN use this TMS to achieve a highly effective utilization of technology for improving our performance. This hierarchy, I don't want to explain more detail about that. This is the important point here. As utility company, PLN intend to develop the technology which is at TRL 7 and want to purchase the technology which is already at the TRL 9. This is the readiness level of technology. So the selected technology in PLN should have a feasibility study for its implementation based on this method, because we have several not good experience that the technology which is successful abroad and other country, it not always success also in Indonesia. So the technology, especially like the ocean energy, is very contextual. So we should have the feasibility study based on the Indonesia context. That the process we do, we several stages, technology roadmap, scanning, screening, assessment, and so on. This is technology roadmap. We do mapping to look at what kind of technology with high impact and with high uncertainty, with low impact, high uncertainty, and so on. We divide it into 4 metrics, divided by 2 indicators: uncertainty or maturity level and impact. This the how we do or more detail, the parameter of impact analysis for energy price, capital cost, fuel cost, OM cost, efficiency, lifetime, capacity factor, load control, construction budget, and so on. And this for uncertainty analysis, resource readiness, technological readiness level, supply chain readiness, public acceptance, integration with the existing system, regulation. Based on that, we put most of the ocean energy conversion technology and ocean thermal conversion still on the quadrant 2, need to improve the maturity. Yeah, indeed, we believe there is some breakthrough coming, and we very welcome. If it is the common data we have here, actually most of the ocean energy still not at the state TRL below 7, only 1 or 2 already reached 8 and 9 TRL. This case already came to us, discuss this some technology for the ocean, maybe last year or several years ago, and we look at the opportunity to build Indonesia, but still have some POC, proof of concept, that the technology will successfully implemented in Indonesia. So we also look to the what kind of technology actually suitable. It's for power, it's for desalination, it's cooling for the oil and gas, aquaculture, shipping, and also and so on. Of course, we look at to the technology for power. And the most important thing, because we install the ocean energy to produce electricity, so we should connect the power station to the grid. And because in Indonesia so far only PLN operate and own the existing grid, you should consider the operating parameters, the grid code of PLN grid system. If we build the new technology, whatever like tidal or wave, we would like to assess. The number 1 is tramping rate. How fast the power plant, the ocean energy technology can go up, go down, by time. And also we need to know how many maximum capacity can be produced continuous rate per unit of technology, and also how many percent the efficiency, and also we should consider maintenance time between failure to look at how many percent the availability factor a year. And number 5, about the capacity factor. It is also very important for us because basically if we connect the power station to the grid, the role of the power station will be base load, will be load follower, will be only picker. Totally different role. So we should divide it. Which is the power station role? And number 6 is about availability factor, is related to the how many hours the availability of this technology year for producing electricity. And also number 7, environmental and social issue. And number 8, this is the last but the most important thing, is about the money. We should meet with the LCOE, levelized cost of energy. I give you the number that basically right now, if you can provide Asia the technology which has the LCOE below or equal to 24 cents per kilowatt hour, is this acceptable for us? And we can go further to discuss more detail about the implementation, about the POC. But if the LCOE is still higher than that, I think, yeah, we have no strong reason, yeah, for discussing more detail about the implementation in Indonesia. As conclusion, as utility company, actually PLN is industrial user. Utilize technology through 2 ways: adoption and incremental innovation, not invention. As power utility company, PLN would like to develop the technology with this at least at TRL7 and want to purchase the technology with TRL9. And PLN has such technology management system for utilizing technology to improve the firm performance. Based on our technology roadmap, most ocean energy still at the quadrant 2, most here. But I believe that there is some breakthrough. However, we open, very welcome from for you all to join together to look at the most feasible technology in Indonesian implementation context. And the number 5, the most determinant factor of Asian energy for connecting to the grid is operating parameter, such as ramping rate, maximum continuous rate, capacity factor, and the last is LCOE. So at the last, I would like to say that some studies say, some experts say that Indonesia has huge potential. For example, for the PV solar, Indonesia has blah, 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 1,000 gigawatt potential. But in reality, we only have less than 1 gigawatt. And also the ocean energy, maybe some experts say, some studies conclude that so many huge potential, blah, blah, blah gigawatt, but so far we have nothing. So please welcome, we can discuss together to realize the first ocean energy in Indonesia. Thank you.
Thank you very much, Dr. Zainal. You have a lot of experience in the electricity utility company, and you have shared your point of view from PLN. We have speaker from a lot of background, from PLN, from the Ocean Developer Technology, and our last speakers, ladies and gentlemen, is from university. Let's move to the next speakers. The last speaker is Prof. Umar Yaakob from University Technology Malaysia. He has several experiences, such as chairman of the UTM Power Professor Council and Deputy Dean Research and Innovation, Head of Department of Marine Technology, Head of the Marine Technology Laboratory, and so on. And he has educational background from University of Newcastle. This afternoon, he will deliver a presentation about selecting technology in the development of ocean energy in tropical waters. So, Prof. Umar, please, the time is yours.
Thank you. Can you see my screen?
Okay.
Okay.
It's clear.
Clear. Okay. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon, or already quite evening here in Malaysia. First, thank you very much to the organizers for inviting me to share whatever I have. First, and I need to give disclaimer here. I'm not going to pour cold water on whatever that has been said throughout the sessions today, because it's been very exciting sessions, listening to the development of the industry. And the second thing I would say is that my experience is mainly in Malaysia. So although it says that selecting technology development ocean energy in tropical waters, my experience mainly in Malaysia, but I have some open source information that I'll share as well. And maybe I'll try to be more realistic and in the presentation to put the other side of the story as well. Okay, I'll cover just very basic 4 points, 2 main points. Number one is just one slide, and I think everybody knows about that already in this session. And then I'll talk about priorities of ocean energy in tropical regions, mainly Southeast Asia, which is where we work, and consideration of technology selection in tropical region, and finally some concluding remarks. So it is, sorry, this is really disturbing. Okay, let's get through that. Okay, so first, ocean energy sources and device concept, I think has been covered throughout this session, so I can skip this one. It's only a one slide anyway. We're talking about different kind of ocean technology, and normally people talk about 5, but there will be 6 and 7 as well. Also has been mentioned earlier by, I think, by Jonas. Yeah. Okay. So I go straight to the main thing that I'm going to share here. Peculiarities of ocean energy in tropical regions. I think, as you are all aware, we go realistically, we have smaller reserve potential in waves and tidal energy. So the tidal and ocean speeds, except for small pockets, tidal range, wave heights, wind speeds are relatively low compared to those of Western Europe and Northeast Asia, Japan, Korea. I share some data that we have. So this is in Malaysia, typically 0.8 to 1.5 knots. So we have about half of that for if you want to take into meter per second. So low current speed average 0.5 meter per second. That's in Malaysia. So here's some simulation that we did using DEF3D. So we found that some parts have above 0.5 meter per second, and small pockets exceeding 1.5 meter per second, but not more than that. Not more than that. So you see the scale there, maximum is 2.5, the red one, 2.5 meter per second. So that is in Peninsular Malaysia. We go to the Borneo region, is similar. There's some parts above 0.5 meter per second, but there are some pockets exceeding 2 meter per second. Of course, we need to go to deep dive to that local parts and really do some measurements in situ and so on. But here we are talking about the globally, that's how we look at our region. Okay, we go, this is tidal range in Malaysia, low tidal range, maximum 4 meter, mostly 2 meters. You see this one is 4 meters, yeah? There's some location with 4 meters. And then we have Bird Island in Passage in the Philippines. There's a long paper here in Chevok, International Conference on Ocean Energy 2016. They say this is the best place that they have, but it's still 1.5 meter per second. It's a very restricted passage in Bird Island Passage there. This one is from Indonesia, UD Sana Energy Procedure. They have some information here. Of course, I know, I think that like Dr. Ahmad Firdaus is talking about Larantuka Straits, there are also Lombok Strait, Alas Straits, and so on. But typically, we will not get very high on average and even maximum. So we have to be careful when we are dealing with the technology. In terms of wave as well, if we see, this is a map you normally use, and in our region, in the southwestern part of Indonesia, maybe we can get up to 20, but within the continental shelf around Borneo, it's below 10 kilowatt per meter. And also here, it's also shown that it's below 10 kilowatt per meter. In blue or in purple, it's all below 10 kilowatt per meter. And we have done our own study as well. This is our own study based on satellite altimetry. In our region is 3 to 7 kilowatt per meter. So all below 10 in our region. And here are some other references which have studied about Malaysian region. And we have within our sea is below 10 kilowatt per meter. Okay, in the Gulf of Thailand, they have wave heights here. HS below 1 meter throughout in the Gulf of Thailand. So it's benign. The same thing here is just 0.33 meters. This is HS throughout the locations in the Gulf of Thailand. In Brunei as well, we have data about wave power here, and it's all below 5 kilowatt per meter. And the tidal range on the right here, the tidal range is also below 3 meters. In Vietnam, we have some data. They have below 5 kilowatt per meter and below 10, depending on the season. We have the monsoon season, the northwestern and southwestern. So that's number one. Basically, we do not have that much potential for wind and for wave and current. So as far as OTEC is concerned, this has the most potential actually in tropical region. In fact, we see the normal when people present about ocean energy or tech particularly, then we can see that the region is mainly in our part of the world, and of course the tropical region will be expected to have more of that. And this part in the Sabah here, Sabah Trough here, is the one that we can focus. This is on the northwestern coast of Borneo. This part, this is Sabah Trough, we call it. This is Brunei. This is Malaysia, Sabah, Malaysia. This will be the whole island of Borneo with Kalimantan down here. So we have studied in UTM this location. We have studied the location and we found that it has enough potential to have that. Okay, so it covers, because Sabah Trough covers as well, go into the Brunei area here. So Sabah Trough, it goes into Brunei. The depth of water here is about 2,000 meters. So it can go down to 2,000 meters, but we need only about 800 meters to get the temperature difference for OTEC. Okay, in the Philippines as well, they say they have a lot of OTEC potential because they have deep waters around the Philippines, and also in Indonesia. Indonesia has the world's largest ocean thermal energy resource, according to one reference. Okay, so that's basically the second point I would mention about something peculiar about a tropical region. Number 3, we have accelerated biofouling and corrosion, as we mentioned earlier as well by some other speakers. According to this paper, accelerated biofouling and corrosion is accelerated by temperature, depth, and light availability. And all this, especially in our continental shelf, we have this problem. And I'll show you one project that we did. This is a UTM, our university project. We put this at sea, and within 6 months, this is what happened. It's very quick for the fouling to come to the platform. Okay, so that's the end of my second part. We go to the third part. Consideration for technology selection in tropical region. Number one, resource device matching is very critical. Dr. Zainal Arifin just now mentioned something about this. Yeah, we need to understand the operational parameters and ensure that devices are compatible with local resource. For example, for tidal current energy device, a cutoff and rated speeds. I think that one, I think Professor Mukhtasar was asking those questions earlier to our friend Simon. And also for wave energy devices are designed to perform in a range of HS and TE. Only low energy devices are suitable because our energy is low. So import of devices designed for other resource categories would be futile. I'm sorry, I'm sounding a bit harsh here, but if you see examples, so there are some criteria here that has been put by people. Wave power should be more than 25 or tax 20, that's good. Tidal barrages 5 meters and tidal current 2 meters per second. These are criteria for stability of resources. The other way of looking at it would be tidal barrage. The present tidal barrages, the mean tidal range is 5.6, 8.5, and 6.4, which is not available in our part of the world. Very difficult. And this is a good paper because it summarizes 14 horizontal axis tidal turbine. It talks about the VR, the rated speed, and also the cut-in speed. Cut-in speed, most of this is above 0.5, which is difficult to find in our part of the world. Just to make the turbine move, not the rated. If you go to rated, even more difficult. Yeah, this rated power is minimum is about 2 meters per second, 2.5, and so on. So this is something that we have to be realistic when we look at our technology. Again, we look at the various efficiencies of the system as well. This is for wind turbine, but of course, it's almost similar when we bring it to, it's not exactly the same, it's similar to when we bring it to sea. I'll show one example here. This is joint probability distribution for Tuas View C, where you see that mainly the HS, they are using TP here, HS 0.5 to 1.5 meter, and TP 5 to 7 seconds. So maximum 1.5. If you go to the Malaysia, this is Malaysia, our wave is in the region of 0.5 to 2 meters and TE of 5 to 7.5 seconds in this region. So if we have two devices, one you import somewhere from somewhere, okay, I call it device X. This device is designed to operate in this range. You know, HS 5.5 to 8 meters and TE 6.5 to 11.5, this region. That's where the full capacity can come in. And so whereas you see the region where we have Malaysian waves it'll be idle. It's not moving a finger even. So whereas this device Y is designed to operate in this HSTP range, so this will be the then it'll fully operate in the region. Although it's a bit small, this is 750 kilowatt compared to 4 kilowatt, but at least it produces 4 kilowatt instead of just standing idle. I need to mention here, sorry, this is an example of a project in Malaysia. Of course, it's a wind turbine, but it's a similar problem when we import a wholesale without looking at the resources. In one island, we have two units, yeah? 2 units of 100 kilowatt turbines, which is just good for tourists. It's not even turning, it's not cutting in even because of the wind speed availability in that region. So it's not properly studied, not properly, but they install it, and they expect to get this kind of energy. Okay, I think that's number 2 will be because of the low density resources. Large commercial scale might not be possible. I could not say cannot, yeah, but maybe it might be a bit more difficult. Most pockets of high tidal stream are located far from national grids. I think Dr. Zainal Arifin mentioned about national grids. The regions of high tidal stream are normally restricted channels, making large scale arrays impossible. In the Philippines, they can afford to put only 3 turbines in San Bernardino Straits 3 times 500 kilowatts. And that's the most that they can put there. And conflicted users also restrict large-scale arrays. For example, this is a study that we did in Malaysia, that the area is so crowded. The area where we can put the whatever turbines and so on are so crowded with all the various multiple users. Okay.
You
yes.
have 1 minute more.
Okay, 1 minute. Okay, thank you. Because of the law and so on, we suggest that hybrid or combined energy system should be there. You know, the 6 thing that I mentioned earlier, we may have small scale combined hybrid for small island communities, could be explored as a way forward. So I'll give you an example of what we did in Malaysia, in Marine Technology Center. We have 2 centers in Malaysia working on ocean energy, one Ocean Thermal Energy Center in Kuala Lumpur, in my university. Both are in my university, but 2 different campuses. So I'm working in Marine Technology Center. This is what we're doing, very small devices. So I just want to share about what we have here. Combined ocean energy system, very small. It's only total is 1 kilowatt. Very much proof of concept. But but it's just as a basis for future development. And we put this at sea. Just show this for a short while. Just we deploy it at sea. This is the one that I think I said earlier. After 6 months, the turbine got stuck because of the fouling, and we have to do a lot of cleaning up. So we have the point absorber with a linear generator. This is a OWC, oscillating water column, and finally this is 7 years turbine here working down there. It's a small. Okay. Concluding remarks. So there is a strong. We need a strong government and political will for small scale development for islands. As I said, maybe economic return might not be good, but still we need to convince the government about the socio-economic imperatives. We still need to develop this, and then we need indigenous R&D activities, developing more relevant devices, energy converters, or modifying those from other regions to suit the resources characteristics in our region. And finally, number 3 will be the networking. Thank you very much. This is part of networking. I'm very glad to be here. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Thank you, Professor. You have very nice speech, because as we know that Indonesia and Malaysia have same characteristic because we are in the same tropical countries. Okay, ladies and gentlemen, now we enter the Q&A session. I will remind to the participant or audience who want to discuss or asking a question, please give the question via chat box, then we will select and deliver to the speakers. We have already some question from the participant. I will pick one first. The first is from Mr. Alicia Shafira to Mr. Ian Johnston. Which one do you think is more applicable and efficient? Building mini grid offshore wind turbines or mega-sized wind farm and conduct energy distribution through subsea cable? Please, Mr. Ian.
Yeah, it's a tricky question because I think there's a place for both. As the previous speaker has said, in fact, the previous 2 speakers have said, we need to look at the whole energy system in each area, so it becomes very specific. So the slide I showed with the sort of concept of a grid across the whole of Indonesia is one option, but equally there will be pockets that require the microgrid solution, and that can be at a scale, and it needs to be scalable. And I think what I was trying to explain in my presentation that and I think was highlighted in the later presentations, that the technology needs to match into the electricity system that's in the area that we need to supply, and that can be a combination of of different technologies and different sizes, and the size needs to be matched to the market or the demand that's there.
Okay, thank you. I think that's clear, the answer. We move to the next question from Mr. Ardi Ardiansa to Mr. Jonas. What is the expected service lifetime, and what kind of mooring component used for the anchoring the device?
Well, first of all, the expected lifetime is 25 years. And if you look at the cost, 75% of the cost is fixed and 25% is service and maintenance over 25 years. That is always included in the LCOE estimates. So that is how the costs are divided. And he also asked about the mooring system, where we have a patented mooring system with floaters on 12 meters depth connected to concrete anchors at the bottom. And that is really the only thing we have down at the bottom, unintelligent concrete anchors. They are only there to keep the floaters in position. And these floaters allow the system to move freely up and down while keeping it on station. So they are patented, this whole function. So I think that was, that answered the first question, yes.
Okay, thank you, Mr. Jonas. I think 25 years is quite long enough because the wave power is working under harsh condition.
Yeah.
Thank you. And the next question for Dr. Ahmad Firdaus. What kind of ocean or tidal current generation technology will SBS use for the Indonesian Strait? Can you explain more specific of the technology? The question is from Mr. Muhammad Sul.
Okay, thank you for the questions. So I think for the Nautilus project, it's already been done the study by the Black and Fetch. They did the study for detailed study for under the maintenance and operational conditions in the Lombok Straits. I think since my research also show the same results actually. So the technology will be used is Atlantis turbines, which is the one that's conducting the projects in the UK. So if you look at the internet, you will find the major projects. This is one of the major projects in the Europe, I think, in terms of tidal energy. So we are going to use that technology in this area. The specification is actually depends on the demand actually. So if the demand it depends on the contract, IPP contract with the PLN. So it's like if they only give for 10 megawatts. So if you see the RPTL, it's like they give the opportunity for only 10 megawatts capacity. So that means maybe we can install two times 5 megawatts turbine capacity in those areas, in which, based on my calculation, will be 24 diameters turbines for those specifications actually. So since this area, so we found some certain areas it's actually quite have energetic flow that's in these locations. So I think this will be good enough for cut-in speeds for those turbine specifications. I think that's. I hope that's answered the question.
Okay, thank you, Dr. Ahmad. I think very site specific the technology. We need to look first which one the location, and we can determine the technology. And the next question for Mr. Jonas again. The question is from Dr. Sony Junianto from Teradaya. Maybe in your PowerPoint there is a power metric for the device, and how to know that the technology can be operated in Indonesia. Maybe if there is in your slide, maybe you can show to us.
Yeah. I think that's quite easy to answer, because if you look at the conditions, what is very specific is the conditions on each site. There is no average general for Indonesia. We have to go in and make a feasibility study, the first feasibility study on each site, because it can vary extremely much from one site to the other. So the feasibility study on each site is extremely important to go in to make the first analysis, because everything is based on the water, on of course the correct depth and an acceptable wave condition that we can see, which is a combination of the wave height, the wave period, and of course the energy content in the waves. So based on this, we can start building up, but we have to see how it looks over time. So we don't just look at a short week, but we have to have a longer period of time, 1 year or 2 year input data. We can get a lot of data from earlier sort of measurements, but we really need that input data for each site to see if it's feasible in exactly that site.
Okay, thank you. I think that's already clear.
Yeah, thank you.
And next question is for Prof. Umar. Every year, the environmental condition is changed. For example, with wind, sea current, and so on. So how to provide equipment device that can absorb in that condition?
I think Ian and Jonas can answer this question better than me. But from my point of view, there's not much change in the way you say environmental conditions. You mean the resources that we have? If you take wave, for example, it won't change much. Maybe throughout the year, yes, it changes. But from year to year, we don't expect it to change that much that it's going to affect the kind of device that we put and so on. It's almost cyclic in the way. Same thing like the ocean current as well, except maybe there is change in bathymetry because of erosion and so on. Otherwise, we do not expect that to change because of the forcing condition will be still the same coming from the sun and from the moon, the gravitational attraction. So unless there is change in bathymetry, and maybe very if changes will be minor, so such as to affect the devices that we plan for many tens of years, I suppose, still will be eligible. I mean, it's still applicable and valid. And that's my point. As far as the ocean OTEC is concerned, again, it is very stable. The sea surface temperature will not change that much. Again, we don't expect to change too much along many years. And the bottom is almost constant because it depends on the depth, water depth. Anyway, thank you very much.
Thank you, Professor. Thank you. OTEC and tidal current, we think that's more predictable than the others. Okay, maybe I will pick one more question, and this is the last question, I think, for this session. The question is from Dr. Erwandi for Dr. Zainal Arifin. Since the maturity of the ocean current technology convert is slow, especially from TRL 7 to TRL 9, many technology cannot pass the valley of death. Does PLN have the ball facing the death valley of the technology? Well, it's quite hard question, I think. Please, Dr. Zainal, can you answer it?
Yes, I think so. Yeah. So far, yeah, I can say that we have no ball facing this serious challenging. Yeah, because it's unpredictable and very costly. Yeah. So in my governance for utilization technology, still we have no option about the strategy for dealing with the death of valley for the new technology for powering in Indonesia. So my question we have no ball for that.
Okay, thank you, Dr. Zainal, for the answer. Okay, ladies and gentlemen, I'm so sorry that not all the questions we can discuss it today. Finally, we reached at the end of the session. However, before we close the ocean energy session, there is a closing statement from Prof. Mutasor, because he is the main chair of the session. So, Prof. Mutasor, I return it back to you, the session. Please, the time is yours.
Thank you, Dr. Dendi Satrio. I would like to extend my thankful to all speakers from many different countries, from Portugal, from UK, from Malaysia, from South Korea, and also from Indonesia, from Sweden also. So thank you very much for the participation. We also thank you very much to the participants for this session, and especially as the committee from the conference, from Ministry of Energy and Mineral Resources of Indonesia, and also from Masyarakat Energi Terbarukan Indonesia, so Indonesian Society for Renewable Energy. We are very grateful for your input, for your discussion. We have very short limited time to discuss very much information, and we believe that we can continue our communication through contact. Maybe from participant can contact to the presenter and also to the committee, and can collaborate. We hope that we can move forward for collaboration and then for implementation. Thank you very much for your effort this afternoon, and I hope that I hope that we had a very good discussion and input. Thank you very much. Good evening.
Thank you.
Thank you.
Thank you.
All right. Assalamualaikum. Thank you very much.
Thank you very much. Assalamualaikum.
Thank you to our honor sponsor Indo EBTKE CONEX 2021, main sponsor by Mentari UK, Indonesia Low Carbon Energy Partnership, platinum sponsor by ISED, also our platinum sponsor by the Swiss Confederation, gold sponsor by Oil Palm Plantation Fund Management Agency, silver sponsor by Swedish Energy Agency and Business Sweden, and Bukit Asam.
The UK and Indonesia are working towards Indonesia's energy transition through the Mentari program. Mentari will deliver inclusive economic growth, electricity access, and support Indonesia's renewable energy ambitions. We work together with the government, financial partners, local communities, and other donors to create jobs, deploy low-carbon energy projects, and fight climate change. The program works through four main areas: policy, brokerage, demonstration project, and collaboration and networking. Furthermore, we strive to mainstream gender and inclusion throughout all our activities. Mentari helps to create a future that is built on low-carbon energy and sustainable economic growth. which belongs to everyone.
The Innovation and Investment for Inclusive and Sustainable Economic Development project, ISED, is a collaboration between the Government of Indonesia and the German federal government, implemented by GIZ and Bappenas, the Ministry of National Development Planning. ISED's private sector-oriented approach emphasizes knowledge and skills transfer, serving as both a leading character and primary focus.
Building new industry requires a collaboration between politicians, society, industry, and people who want to develop a better world.
The transformation will go much faster than we believe just now.
100 years ago, we started to explore. We have transformed into a world-class energy company. We proudly present for Indonesia, energy for a better life. Bukit Asam, beyond coal.
Open your eyes. Look around. The Earth needs us to save it from climate crisis. The question is, can we make a brighter future for the world? Yes, we can. From the soil we stand on lies a better solution for mankind. The Earth provides magnificent geothermal energy that is clean and renewable, bringing eco-friendly resources from underneath, transforming sustainable energy for the benefit of society, working hand in hand meticulously, balancing the life of nature, preserving natural biodiversity in its pristine environment, creating valuable harmony that lasts for generations, providing comfort for all living beings, advancing life without leaving nature behind. We connect people and their surroundings while empowering Indonesia's economic growth and implementing new geothermal technologies. Working with the brightest stars that drive us forward. Perfecting excellence in everything we do. And shifting the future of humanity one step at a time. We have been making our steps, leaving marks for a better future, and heading for what's next, to make tomorrow brighter.